Hello, I'm Michelle Crummell, and in this lesson we are going to learn about the quotient rule, which will help us find the derivative of functions that are written in the form of a quotient. In activity 1, we're going to establish the need for a special quotient rule. So let's suppose we have two functions u and v. The function u of t equals 2t squared, and then the function v of t equals t cubed plus 4t. We're going to find the derivative of u and the derivative of v, and we can do that using the derivative rules we have already learned. So we know that u prime of t equals 4t by using the constant multiple rule combined with the power rule. And we know the derivative of v prime of t equals 3t squared plus 4, again using the power rule, the constant multiple rule, and the sum difference rule. So we have the derivative of the function u, and we have the derivative of the function v. Now let's consider this new function, which is formed by taking v and dividing it by u. So we're calling this new function q of t. You can think of the q as quotient. So this function is a quotient. It's the quotient of v over u. We're going to rewrite the formula for q by dividing each term in the numerator by the denominator and simplifying. So in other words, we're going to split this into two fractions where we have t cubed over 2t squared. Q of t equals t cubed over 2t squared plus 4t over 2t squared. So observe, if this is what we had started with, there is a common denominator, so we could always add it back together and get the original form of q of t, which was t cubed plus 4t in the numerator and 2t squared in the denominator. But now that I have written it in this way, I can simplify it algebraically. Q of t equals t cubed divided by 2t squared simplifies to t over 2. And t divided by 2 is the same as 1/2 times t. Plus, and then the next term, 4t divided by 2t squared simplifies to 2 divided by t. 2 divided by t like this, but I can also rewrite that as 2 times t to the power -1, right? If I move the t up into the numerator, then I would change the exponent from a +1 to a -1. So 2t to the -1. And the nice thing about writing it this way is that I can now find the derivative using the sum and constant multiple rules combined with the power rule. So now we have q prime of t equals, the derivative of 1/2 t is 1/2, and the derivative of 2t to the -1 is -2t to the -2. So -2t to the -2, t to the -2 is the same as 1 over t squared. All right, so now I have q prime of t. That's my derivative there. So we've taken care of parts A, B, and C. Part D says, is this statement true or false? The derivative of v over u is equal to the derivative of v over the derivative of u. Well, what is the derivative of v over u? That's the derivative that we just found. That's the 1/2 minus 2 over t squared. Is that equal to, that's what we're trying to figure out, true or false, is that equal to the derivative of v over the derivative of u? Well, here's the derivative of v up here. We found that to be 3t squared plus 4 over, and then the derivative of u is right here. We found that to be 4t. Are these two expressions equal? Well, they don't look equal, but it could be that, we just haven't fully simplified one side or the other. Are they equal? Well, I could disprove this just by coming up with one example, one value of t that makes this false. So let's just try t equals 1 and see what happens. at t equals 1, on the left-hand side, we get 1/2 minus 2. And is that equal to the right-hand side? On the right-hand side, when t is 1, we get 3 plus 4, which is 7, over 4 times 1, which is 4. And 1/2 minus 2 is not equal to 7 over 4. So this statement in general is not true. It might be true for some value of t, but it's not true in general. We showed that it's definitely not true when t equals 1. There's lots of other t values we could have tried. And it's worth noting here that if I had chosen a t value and it worked, that doesn't prove that the statement is true. That would only prove that it's true for that one specific t value, right? It's not sufficient to prove something is true using one example, but it is sufficient to prove something is false using one example. All you need is one example that shows that it's false, and then you know in general it's false. So this is a false statement. That means that if you want to take the derivative of a quotient, like this right here, this is a quotient. If you want to take the derivative of the quotient, you cannot, okay, this is a big no-no. You cannot simply take the derivative of the numerator and divide it by the derivative of the denominator. That will not give you the right answer. Hence, we need a special way to take the derivative of a quotient. We sort of got around the problem in this example by rewriting q of t in a different way so that it wasn't a quotient, right? We rewrote it in this way right here so that we could apply different derivative rules instead. But if we wanted to leave it in quotient form, we don't have a way to get the right answer to try and get the derivative. So we're going to develop a rule that we can use that will help us take the derivative of a quotient. The quotient rule says if h of x equals f of x over g of x, then h prime of x equals f prime g minus f g prime over g squared. And that may seem like a lot to have to remember, but it is similar in structure to our product rule. Remember, if we wanted the derivative of f of x times g of x, I'm just going to abbreviate fg. If I wanted that derivative, the derivative of f of x times g of x, it would be f prime g plus fg prime. So you'll notice with the quotient rule, we start out with f prime g and then minus fg prime, so it's similar in structure, and then all of that is divided by g squared. So I don't find it too difficult to memorize the quotient rule if I've already memorized the product rule. F over g prime equals f prime g minus fg prime over g squared. And in our product rule lesson, I talked about the fact that it's not always a great idea to memorize formulas just in terms of the letters that are being used, because our functions could be called by other names. We could encounter a function where g of x was in the numerator and f of x was in the denominator, and if you just memorize the quotient rule using f's and g's, that is going to mess up the answer. So when I think quotient rule, instead of thinking f's and g's, although I do often think of it that way because I do have it memorized that way, but more often than not, when I'm sort of working out a problem in my head, I'm not saying f prime g minus fg prime over g squared. I'm saying to myself, derivative of the first times the second. Nope, sorry, numerator, denominator, right? So I say top and bottom. A lot of people don't like that slang, because the numerator should be called numerator mathematically, right? And the denominator should be called denominator. But if it's just in my head and I'm not writing it down formally on my paper, then I think it's fine to refer to that as top and bottom. So I say to myself, derivative of top times the bottom minus the top times the derivative of the bottom all over the bottom squared. That's what I'm saying to myself when I'm working out quotient rule. Okay, so if you're still kind of not sure which one to start with now that we're learning all of these rules, you start with by taking the derivative of the very first thing that you see. And that's true with the product rule as well, right? Just the very first part of that product, you start by taking the derivative of that. And in the quotient rule, the very first thing you have in your quotient, you start by taking the derivative of that. Okay, so start with derivative of the top times the bottom minus top times derivative of bottom over bottom squared. Here's just another way to write the quotient rule using letters other than f and g, because of course functions can be called by other names, but it's really the same rule. Let's look at an example. Use the quotient rule to find q prime of t if q equals the quantity t cubed plus 4t over 2t squared. Now this is the same function, by the way, that we saw in this last problem here. That's our q of t function. So now we're going to take the derivative using the quotient rule instead of the other way we tried to do it, where we separated this into two fractions, rewrote it algebraically, and then used the power rule and some of our other rules. So let's just tackle this one using the quotient rule. So I would say q prime of t, because I'm taking the derivative of q of t, so that would be proper notation, q prime of t. Or I could also say dq over dt if I wanted to use Leibniz notation, but we'll stick with q prime of t here. We start by taking the derivative of the top, so the numerator. Okay, I'm going to color code this. Numerator in green and denominator in blue. So we're going to start with the derivative of the top. And I'm actually going to write before, like normally I would just do this in my head. I know the derivative of t cubed plus 4t is 3t squared plus 4, but I'm going to write out the steps. So it's probably a good idea to have it written out in your notes. And sometimes when you're doing quotient rule, and you have a lot of terms in your numerator or denominator, it is helpful to write this down step by step. So derivative of the top, I'm going to actually write the top in brackets and then put the derivative symbol outside. So I haven't taken the derivative yet, but this is to remind me that that's what I need to do. I need to take the derivative of t cubed plus 4t and then multiply it by 2t squared minus, and then I'm going to keep the top, so t cubed plus 4t, leave the numerator alone, multiply that by the derivative of the denominator, so derivative of the bottom, all over bottom squared. Okay, and now we'll work it out. So the derivative of t cubed plus 4t is 3t squared plus 4 times the 2t squared. I'm going to run out of room here. Let me resize this a little bit. Okay, so derivative of t cubed plus 4t is 3t squared plus 4. We multiply that by the 2t squared minus, then we're going to keep the t cubed plus 4t and multiply by the derivative of 2t squared, which is 4t. And all of that over 2t squared. Squared is 4t to the fourth. So that is my answer. Now, I certainly could simplify this some more. If I distributed terms, I might have some like terms that I can combine, but that is the answer to this problem. That is the derivative. So we're not going to take the time to simplify that here. Let's practice a few examples. The derivative of x over e to the x. So we have this other notation here. I hope you're getting comfortable with the multiple ways to write derivatives. So d over dx of x over e to the x. We want the derivative of x over e to the x. So this means find the derivative of x over e to the x. And if we use the quotient rule, that is derivative of the top. I'm going to write it out before I take the derivative. Derivative of the top times the bottom minus the top times the derivative of the bottom over the bottom squared, like so. Okay, and now we can compute. So the derivative of x is 1 times e to the x minus x times the derivative of e to the x. The derivative of e to the x is e to the x over e to the x squared. When you have a power raised to a power, you multiply exponents, so that's e to the 2x. All right, e to the x minus x e to the x over e to the 2x, and that matches choice B. If f of 3 equals 2, f prime of 3 equals 4, g of 3 equals 1, g prime of 3 equals 3, and h of x equals f of x over g of x, then what is h prime of 3? To find h prime of 3, the first thing we have to do is find h prime of x. So here is my equation for h of x. We want to find the derivative of that. What is h prime of x? Well, this is a quotient, so let's use the quotient rule. Derivative of the top times the bottom minus the top times derivative of the bottom over bottom squared. Now, to find h prime of 3, we simply need to substitute 3 in for x. So f prime of 3, g of 3, minus f of 3, g prime of 3, over g of 3 squared. And then we substitute in. F prime of 3 is 4, g of 3 is 1, f of 3 is 2, g prime of 3 is 3, g of 3 is 1 squared. So that is 4 minus 6, or negative 2. If f of x equals x over sine x, then f prime of x equals, so this is a quotient. We're going to take the derivative using the quotient rule. So the numerator is x, and the denominator is sine of x. So our derivative is the derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. Sine squared x, like so. Okay, derivative of x is 1. 1 times sine of x minus x times the derivative of sine x is cosine x over sine squared x. Now, there are ways we could simplify this, but I think this does match answer choice A, so we will go with that. Let's try some graph problems. So p of x is defined as f of x over g of x. Find p prime of 5. So to find p prime of 5, we first find p prime of x. P prime of x, we're taking the derivative of p of x right here, is f prime g minus f g prime over g squared. So I kind of took a shortcut in my function notation, which I don't know if that was wise because we need p prime of 5 and you've sort of lost sight of where the 5 is going to go. But it's f prime of 5, g of 5 minus f of 5, g prime of 5 over g of 5 squared. And we're going to read these values, hopefully be able to, from the graph. So f prime of 5, here's f of 5, but f prime of 5 would be the slope of the graph at that point. And the slope, since that's on a linear piece, is easy to figure out just using rise over run. We go down 1 and right 2. So the slope is negative 1/2. Negative 1/2 times g of 5. G of 5, we'll read from the graph right here. G of 5 equals 5. Minus f of 5. F of 5, that's the point I indicated earlier. F of 5. Oh, f of 5 is not a whole number. It is negative 3.5. So plus 3.5 times g prime of 5. G prime of 5 is referring to the slope at that point where x equals 5. And the slope there is 1. So that's easy. And then all of that has to get divided by g of 5 squared. G of 5 is 5, and we're going to square that to get 25. Okay, so we have negative 1/2 times 5, which is negative 2.5 plus 3.5 is 1 over 25. So p prime of 5 equals 1 over 25. So we have this part, p prime of 5. But then we're also asked to find the equation of the line tangent to the graph of P when x equals 5. So I need the tangent line equation. To write the tangent line equation, I need, at the point where x equals 5, I need to know P of 5 and P prime of 5. We've already found P prime of 5. Now we need to find P of 5. And we find P of 5 using the equation for P of x. So P of 5 equals f of 5 over g of 5. So f of 5, that's my negative 3.5. I probably should write that as a fraction because I have to divide that by something. And then g of 5 is equal to 5. Okay, so negative 3.5 is negative 3 and 1/2, so that's negative 7/2. Divided by 5 is the same as times 1/5, so that's negative 7 over 10. Okay, equals negative 7 over 10. So my point of tangency, I've got P of 5, let's just summarize. P of 5 equals negative 7 over 10, and P prime of 5 equals 1 over 25. Those are the two things I need to write the equation of my tangent line. So it's y equals the y coordinate, 7 over 10, plus the slope times x minus the x coordinate. So there is my tangent line equation. Y equals 7 over 10 plus 1 over 25 times the quantity x minus 5. Let r of x equal sine of x over f of x. Find r prime of 0. So first we find r prime of x. R prime of x equals, we're going to use the quotient rule here. So it's the derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. R prime of 0, oh, well, let me finish. I haven't taken the derivative yet. The derivative of sine is cosine. So cosine x times f of x minus sine x times f prime of x over f of x squared. Okay, now r prime of 0, we're going to substitute 0 in for x into that derivative equation. So it's the cosine of 0, which is 1, times f of 0, minus the sine of 0 is 0 times f prime, so just 0, over f of 0 squared. So it's f of 0 over f of 0 squared, which is just 1 over f of 0. And f of 0 we can read from the graph. F of 0 is negative 5. So it's 1 over negative 5, or negative 1/5. Find the equation of the line tangent to r when x equals 0. So I've already found r prime of 0. We've got r prime of 0 equals negative 1/5, but we also need r of 0 if we're going to write the equation of the tangent line. So for r of 0, we're going to come back to the equation for r of x and let x equal 0. R of 0 equals the sine of 0, which is 0, over f of 0. So that's just going to be 0. And then we can write our tangent line equations. Y equals the y coordinate, which is 0, plus the slope, which is negative 1/5, times x minus the x coordinate. The x coordinate is also 0. So just y equals negative 1/5 x. Let's try some table examples. Let f and g be differentiable functions. Estimate the value of g prime of 2.5. So we have g prime of 2 given. We have g prime of 3 given. We're trying to figure out g prime of 2.5. And we're not going to be able to figure out exactly what it's equal to, but we can estimate the value using a central difference. So we take the closest two surrounding points to x equals 2.5, which would be this 2 and this 3. And we estimate the slope of g using the values for g of x, right? So we're going to use the point 3 comma negative 3 and 2 comma negative 1. So g prime of 2.5 is approximately equal to, so I'm going to go a little bit past the 2.5, which would be the 3. So negative 3 minus negative 1 over 3 minus 2. And that's going to be negative 2 over 1, or negative 2. That is our estimate for g prime of 2.5. Number 2, if p of x equals g of x over f of x, so here's where you might run into trouble if you memorize your formula using f's and g's, because the g is now in the numerator and the f is in the denominator. Okay, so this is tricky. If p equals g over f, what's the value of p prime of 4? So let's find p prime of x, and then we can substitute the 4 in for the x. P prime of x, it's the derivative of the top, so g prime of x, times the bottom, f of x, minus the top, g of x, times the derivative of the bottom, f prime of x, over bottom squared, f of x squared. Okay, now we can substitute 4 in for x and get p prime of 4 equals g prime of 4. So g prime of 4, right here, negative 2, times f of 4. F of 4 is 1, minus g of 4. G of 4 is 7, times f prime of 4, 8, over f of 4. F of 4 is right here, squared. It's always nice when you just have to divide by 1. So negative 2 minus 56, or negative 58. P prime of 4 equals negative 58. What does this value say about the graph of p when x equals 4? Well, if the derivative of p is negative at this value of x, then p is decreasing at this value of x. P is decreasing at x equals 4, since p prime of 4 is less than 0. If q of x equals 2x squared times f of x over g of x, what is the value of q prime of 2? Well, we're going to have to use a lot of different derivative rules to find q prime of x, because q of x is a product. Here's the first factor, here's the second factor, but then the second factor is a quotient. So we're going to have to use product rule, and then as part of the product rule, we're going to get to a step where we're going to have to use the quotient rule. So in this problem, we've got quotient rule inside of product rule, and then we're also using constant multiple rule and power rule. So lots of derivative rules on this one. Let's go ahead and start with our product rule. So q prime of x equals the derivative of the first factor, which is 4x, times the second factor, f of x over g of x, plus the first factor, 2x squared, times the derivative of the second factor. So the derivative of the second factor is the derivative of f of x over g of x. And to find that, we need to use the quotient rule. F prime of x times g of x minus f of x times g prime of x over g of x squared. So there's my equation for q prime of x, and I really want q prime of 2. So for q prime of 2, we substitute 2 in for x. 4 times 2 is 8. So I have 8 times, and then it would be f of 2 over g of 2. F of 2 is 2. G of 2 is negative 1. okay, plus 2 times 2 squared is 8, times, and then we have f prime of 2. F prime of 2 is 9, times g of 2, which is -1, minus f of 2 is 2, times g prime of 2 is -1, over g of 2 is -1 squared. And let's simplify that. So 8 times 2 over -1 is -16, plus 8 times, and then we have -9 plus 2 is -7. Okay, so that would be -16 minus 56 is -72. -72. The equation of the tangent line to V, we need to know V of 3 and V prime of 3 so that we can write our tangent line equation. So for V of 3, we're simply going to substitute 3 in for x. 3 times 3 is 9 over G of 3. G of 3 is -3. So we've got 9 over -3 or -3. Okay, so V of 3 equals -3. That's one thing we need to know for our tangent line equation. The next thing is V prime of 3. So for V prime, we're going to need V prime of x first, and we're going to use the quotient rule on 3x over g. So it's the derivative of the top times the bottom minus the top times derivative of the bottom over bottom squared. Okay, so V prime of 3. Nope, I haven't taken the derivative yet. Derivative of 3x is 3. So it's 3 times g of x minus 3x g prime of x over g of x squared. Now I want to find V prime of 3. So let me come back over here. V prime of 3 equals 3 times g of 3. G of 3 is -3. Minus 3 times 3 times g prime of 3. G prime of 3 is 6 over g of 3 squared. So g of 3 is -3 squared. Okay, so it's -9, and then I have 3 times 6. So 9 times 6 is 54. It's 54 over 9. All right, so that is -63 over 9 is -7. So that is V prime of 3. Now to write our tangent line equation, just come up here. Y equals the y value, -3, plus the slope, which is here, -7, times x minus the x coordinate, which is right here. So y equals -3 minus 7 times x minus 3. Use the quotient rule to find the derivative of each of the following functions. So before we get started on this, we want to remember that the derivative of sine x is cosine x, and the derivative of cosine x is negative sine x. We're going to be using those derivative rules when we derive the formulas for the derivative of tangent, cotangent, secant, and cosecant. Okay, so we already know the sine cosine rule. We're going to derive formulas for the derivative of the other trig functions. So for y equals tan x, let's start by writing that as sine x over cosine x. The tangent of x equals sine x over cosine x. That is a quotient. So the derivative, y prime, equals, we're going to use the quotient rule here. It's the derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. The derivative of sine x is cosine x, so we have cosine x minus sine x. The derivative of cosine x is negative sine x, and then over cosine squared x. So we have cosine squared x plus sine squared x over cosine squared x, and we can use a trig identity in the numerator. Cosine squared x plus sine squared x equals 1. And we'll use another trig identity. So the reciprocal of cosine x is secant x. So 1 over cosine squared x is secant squared x. And that is the derivative of tan x. The derivative of tan x is secant squared x. You do need to memorize this formula. The derivative of tan x is secant squared x. If you don't memorize it, I guess it's okay, but you're going to have to do all of this work every single time you're asked to find the derivative of tan x. Let's try cotan x. So the proof there will be similar. We can rewrite the cotangent of x as cosine x over sine x. So y prime equals, we're going to use quotient rule. It's the derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. Derivative of cosine is negative sine, so negative sine x minus cosine x. The derivative of sine x is cosine x over sine squared x equals negative sine squared x minus cosine squared x over sine squared x. We can factor negative 1 out of the numerator, and we have left sine squared x plus cosine squared x, which becomes 1. So we have negative 1 over sine squared x, which is equal to negative cosecant squared x. That is the derivative of cotan x. It's negative cosecant squared x. The derivative of y equals secant x. You can write secant x as a quotient if you write it as 1 over cosine x. And then we can use the quotient rule. So y prime, again, it's the derivative of the top times the bottom minus the top times the derivative of the bottom over bottom squared. So derivative of 1 is 0, which is going to just make that whole term equal to 0. The derivative of cosine x is negative sine x. So I have negative sine x over cosine squared x. And we could leave the answer like that, but generally we do some simplifying here. This is equal to sine x over cosine x times 1 over cosine x, which is equal to tangent x secant x. That is the derivative of secant x. Okay, we've got one more. We want the derivative of cosecant x. So we rewrite it as a quotient, 1 over sine x, and then we take the derivative using the quotient rule. So it's the derivative of the numerator times the denominator minus the numerator times the derivative of the denominator over denominator squared. Derivative of 1 is 0. So this first term just goes to 0. Derivative of sine x is cosine x. So we get negative cosine x over sine squared x, which we can rewrite as negative cosine x over sine x times 1 over sine x, which we can write as negative cotangent x cosecant x. And that is the derivative of cosecant x. Okay, so let's write those again. Derivative of tan x, secant squared x. Derivative of cotan x, negative cosecant squared x. Derivative of secant x, tangent x. And derivative of cosecant x, negative cosecant x, cotangent x. Now, you do need to memorize these derivative formulas. We have a long list of derivatives to memorize. If you don't memorize them, again, it's okay. You're just going to spend a lot of time on your assessments trying to derive these formulas, and you won't have enough time left over to actually complete the problems. So it is highly recommended that you memorize. Same for the AP exam. Just memorize these formulas. I do have a mnemonic device. I have a mnemonic that you can use to help you remember these derivatives. Okay, so it's sexy, sexy tan. I'm going to write it out. Sexy, sexy tan minus kissy, kissy cot. And what that is supposed to represent, sexy is supposed to represent secant x. Secant x. And then tan, of course, represents tangent x. Minus kissy is supposed to represent cosecant x. Cosecant x, and then cot is supposed to represent cotangent of x. Okay, how does this help with the derivatives? Well, they're written in order, so you can read this left to right, or you can read this right to left. If you want the derivative of secant, it's equal to secant x tangent x. Okay, if we look back up here, we can see that. The derivative of secant is secant tangent. So if you can remember sexy, sexy tan, then you can remember that the derivative of secant is secant tangent. Sexy, sexy tan. Derivative of secant is secant tangent. Likewise, the derivative of cosecant is cosecant cotangent, but you have to remember the negative sign. It's negative. All of the cos are negative. The derivative of cotangent x is negative. The derivative of cosecant x is negative. The derivative of cosine x is negative. All of the cos, the three cos, their derivatives are negative, so you just have to remember that. All right, so again, going in this direction, derivative of secant is secant tangent. Derivative of cosecant is negative cosecant cotangent. But what's neat about this trick is that you can also read it backwards. So let me undo my underlines. If we go backwards, the derivative, so I'm going in this direction, the derivative of cotangent is right here, negative cosecant squared x. And the derivative of tangent right here, secant squared x. Okay, so that might help you remember these trig derivative rules. Find the equation of the line tangent to g of x at x equals negative 2, where g equals 3x minus 1 over x plus 3. So we're going to go ahead and use the quotient rule to take this derivative. The numerator is 3x minus 1. The denominator is x minus 3. So g prime of x, it's the derivative of the top. I'm going to just write out the steps first. When I'm solving problems, I normally don't do this extra step, but it's good for your notes to have it like this. And then the top times derivative of the bottom over bottom squared. That's what we need to do in order to take this derivative. Okay, so here we go. The derivative of the top is 3 times the bottom minus the top times the derivative of the bottom is just 1. Don't really need to write that. Over bottom squared. Okay, so that's g prime of x. Now we need g prime of negative 2. So it's 3 times negative 2 plus 3 minus 3 times negative 2 is negative 6 minus 1 is negative 7 times 1 over negative 2 plus 3 is 1 squared is just 1. So 3 plus 7 is 10. That's g prime of negative 2. Okay, so we've got g prime of negative 2 equals 10. We also need to know g of 2 in order to write our tangent line equation. And we can get that from g of x by letting, negative 2, not positive 2. Negative 2, by letting x equal negative 2. So 3 times negative 2 minus 1, negative 7, over negative 2 plus 3 is 1, so negative 7. Okay, and then our tangent line equation, y equals the y coordinate plus the slope times x minus the x coordinate, right there. So y equals negative 7 plus 10 times the quantity x plus 2. Find the equation of the line normal to g of theta equals 3 theta over cosine theta at theta equals pi. So to find the equation of the tangent line, we need to know what is g of pi and what is g prime of pi. But for the normal line, we're going to use the opposite reciprocal slope. So that would be opposite reciprocal of g prime of pi. Okay, so this is actually what we need to write the equation of the normal line. Let's start by finding g of pi. For g of pi, we simply need to substitute pi in for theta in the equation for g of theta. So g of pi equals 3 pi over cosine pi. Cosine of pi is negative 1, so this is equal to negative 3 pi. So we've got that, negative 3 pi. Now let's find g prime of pi, but before we can do that, we have to find g prime of theta. And for that, we're going to use the quotient rule. Okay, so it's the derivative of the top, which would be 3, times the bottom, minus the top, times the derivative of the bottom, which is negative sine theta, over bottom squared. Then we substitute pi in for theta. 3 times the cosine of pi plus 3 times pi times the sine of pi, which is 0, over the cosine of pi squared, which would be negative 1 squared. So that is just negative 3 plus 0 divided by 1, or negative 3. And if g prime of pi is negative 3, that's the slope of the tangent line, then the slope of the normal line is the opposite reciprocal, or 1/3. So our tangent line equation would have a slope of negative 3, but our normal line equation has a slope of 1/3. So let's write normal line. Y equals, it's the y coordinate from that point of tangency, negative 3 pi, plus the slope, and for the normal line, we're using 1/3 as the slope, times x minus the x coordinate, which is pi. For our last set of problems, you may want to pause the video and try this on your own. So these are all problems where the best way to take the derivative is to use the quotient rule. Thanks for joining today, and in our next lesson, we're going to take a look at the chain rule.